have with me a rectangular frame on which I have wound a coil of wire. In the last lesson we found that if such a coil is rotated in a magnetic field, imagine that there is a magnetic field directed from the floor to the ceiling. There are lines of force going from the floor to the ceiling. If I rotate this inside that magnetic field, this coil will be cutting the lines of force. And when you keep rotating it, the rate at which the lines of force will be cut will be different for different angles. Now, the angle we will be considering here is the angle between the normal to the plane of the coil and the magnetic field. Well, we know that as the flux linked with the coil changes, that change in the flux will induce an EMF in the coil, and hence a current will flow. When the conductor is moving down, if the induced EMF is in one direction, when it moves up, the direction will change. That means for one complete rotation of this coil, the direction of the induced EMF will change completely. Now, this is how alternating current is generated. So that's the theme of our discussion today. Alternating current. A coil rotating in a magnetic field will have a current induced in it. When the coil rotates inside the magnetic field, here I have represented a magnetic field that is directed from left to right, and we have a coil that is rotated in. The flux linked with the coil changes continuously, and this induces an EMF in the coil. That's what we have been talking about so far. However, there is another way to change the flux linked with the coil. You can keep the coil stationary and rotate the magnetic field. So, the flux linked with the armature coil, the coil wound on a frame is actually called the armature coil. The flux linked with the armature can also be changed by keeping the coil stationary and moving the magnetic field. Now, for each rotation of the coil, the direction of the induced EMF and hence the direction of the current will change. Now, such a generator is called an AC generator. I have a diagram here. You can see the direction of the magnetic field and the coil, and look at the angle theta. Now, if this is the plane of the coil, this is the normal to that plane, and this is the direction of the magnetic field, and this is the angle theta. Angle theta is the angle between the normal to the plane and the magnetic field. That means at any given instant, the flux linked with that coil will be B times cos theta, and of course if the coil has n turns, the total flux linked with that coil will be n times B cos theta. Well, at any given time, the normal to the plane of the coil makes an angle theta with the direction of the field. That means phi b, the flux linked with that coil, the total flux linked with a coil like this will be n the number of turns times a times b cos theta, where a is the area of the coil. Well, this we have discussed already. As the coil rotates, the angle theta is a function of time and can be written in terms of the angular frequency as theta equal to omega t. Now, you must understand that the magnetic field does not change. When the coil rotates, the magnetic field remains a constant. So what changes is the angle theta. Angle theta is a function of time, and we write it as theta equal to omega t, where omega is the angular frequency, which you are familiar with. Now, therefore, the flux linked with the coil can now be written as phi b equal to NAB cos omega t. As the coil is rotated in the magnetic field, the flux linked with the coil changes, and the induced EMF will be a measure of the rate of change of flux linked with it. And that is Faraday's law of electromagnetic induction. Well, you know that phi b equal to NAB cos omega t, and the induced EMF is negative of d phi by dt. Of course, the negative sign comes from Lenz's law. Now, that means the derivative of this quantity with respect to t, NAB is a constant, and the derivative of cos omega t will be negative omega sine omega t. I hope you have no problem there. So the two negatives will combine. That gives you the induced EMF in the armature coil is NAB omega sine omega t. Now, I would like you to have a look at this. When the coil rotates, the variable here is that angle, which is omega t. Now, what is the maximum value of that EMF? The maximum value of the EMF occurs when that angle is 90 degrees. That is, the normal to the plane of the coil and the magnetic field are at right angles. You see, if the lines of force are now like this, that will be the time the coil will be cutting the maximum number of lines of force. The rate of change of flux will be maximum when the angle is 90 degrees. At that time, sine omega t is 1, or the maximum induced EMF will be NAB omega. So this quantity can now be called E max. Is that right? So I can say induced EMF E is E max, maximum EMF, times sine omega t. Or the induced EMF therefore is a function of time. It is a sine function. Now, when the coil moves up, if the induced EMF is from A to B, you see, if the coil moves up, what I mean is this side moves up. If the induced EMF is from A to B, on the top side, when that side moves down, now watch it here, this is the side I'm talking about. When that side moves up, if the induced EMF is from A to B, as it moves down, the induced EMF will be from B to A. That's something that you need to really understand. Now, for each rotation of the coil, the direction of the induced EMF and hence the direction of the induced current will reverse, and that's why we call it the alternating current. The number of times the direction of current reverses per second, which is the same as the number of rotations per second, is called the frequency of the AC. The normal AC that we use in our homes and offices has a frequency of 60 Hertz. That means the coil that generates the current will rotate 60 times inside the magnetic field. Alright. The frequency F and the angular frequency omega are related. Can you tell me what a relation is? We have been talking about it from Physics 1. That relation is omega equal to 2 pi f. You cannot forget that relation. Now, since E equal to NAB omega sine omega t, the maximum value of E occurs when sine omega t is 1. And we will represent this quantity NAB omega as E max because that is the maximum value of the EMF. And so we can write E max is NAB omega, where of course omega is 2 pi f. we can now write E of t, the induced EMF at any given time, is E max times sine omega t, that omega is replaced by 2 pi f. This induced voltage gives rise to an induced current. Now, if this is the induced EMF, can you write the expression for the induced current? It will be a similar expression. I, as a function of time, will be I max sine 2 pi ft. So this is the equation for the induced current, which is actually derived from the equation for the induced EMF. Well, the figure illustrates how the voltage changes with time. The voltage is a sine function. You can see this is how the voltage changes for one complete rotation of the coil, and that time is called the period. And of course that the maximum current or maximum EMF is the amplitude or the peak voltage. The peak voltage is from the negative maximum to the positive maximum, or that's the peak to peak voltage. Now, when the plane of the coil is perpendicular to B, theta equal to 0, and no change in flux occurs, and the induced voltage is 0. We talked about this already, so we don't need to do that again. How the voltage changes from 0 to a maximum, then back to 0. You can see here, now, the induced EMF at this position is actually 0. Now, the induced EMF increases, reaches a maximum when the number of lines of force cut are maximum, and then the coil begins to rotate in the opposite direction. The EMF increases in the negative direction and comes back to 0 when the rotation is complete. So once again, the induced EMF is 0, maximum, 0, negative maximum, and back to 0 for one complete rotation. Alright. Now here you have an illustration of how that happens. As this coil is rotated in the magnetic field, the EMF increases to maximum, to 0, negative maximum, 0, and it continues. Well, that is a good illustration of how the alternating generator works. Now, when we talked about direct current circuits, we had a symbol for representing a battery. In the same way, when we use an alternating current source, we will use the symbol. This is the symbol for an alternating current. We will be using this very often in this lesson. So we will also refer to this as the generator that generates the alternating current. In an alternating current circuit, we use this symbol in place of